In our remaining 10 minutes, could you take some time and discuss some recent projects that you've been involved in for NPR?
Sure, I'd love to. I'll show you a couple of different kinds of examples. Um, this was really interesting. This is a great example of a product where there was not sufficient design for manufacturing that was done. This is an interesting device. It's a wound care clamp. You can see it has some pointy, sharp needles at the bottom. And what this device does is seals a traumatic injury. Think about a puncture wound or a gunshot. It was actually designed by a military emergency physician from the Canadian Armed Services. It's in use today by United States Special Forces and was just approved for broader use in the military last year. So it's a simple device, but extraordinarily clever to close. The needles grab the skin, close a wound, stop the bleed. It takes the place of what you'd otherwise use a tourniquet on extremities, so think arms and legs, but can also be used on head, chest, etc. The device on the bottom, they didn't give it sufficient thought in terms of design for manufacturing and cost, etc. So they came to us with a product that cost $22 a piece to make. Keep in mind, this is a single-use device, so you want to sell it for 20, 25 bucks a piece. It's going to be used once and thrown away. You can see the device on the bottom has some metal parts, etc. The one on the top is how we redesigned it. Their goal was, can we get this down to a cost of $15 a piece? We got it through some clever engineering down to about $8 a piece. So this was a great example. Took about a year to redesign it and get it back into production. Significantly reduced the cost and improved the performance while we were at it. So very interesting, clever device, and satisfying to know that's out there in the world saving lives today. This is another interesting device. This surgical assist arm came to us in a prototype form as a product that was designed by an engineer from Stanford University. What it does, I'll use my cursor to point to the end of the arm where you can see a button outlined in blue. What this does is the button is depressed. You can see the joints in the arm. They're flexible. You press the button, it releases a electromechanical mechanism that enables a surgeon to position that arm wherever it needs to be. You release the button, it locks in place. You can see this device is holding what's called a retractor, which might be used to hold open a surgical site on a patient. Typically, that would be done by a nursing aide who's standing there for maybe hours just holding that retractor in place. So this device came to us in prototype form. It functioned, but had not been designed for manufacturing. So you can see there's lots of mechanical metal components here, all of which had to be detailed out, all the tolerances that we talked a little bit about earlier for how all these parts fit together so that they can be assembled and function reliably. All of that had to be worked out. There are issues around selection of materials, the finish on all of these elements that had to be worked out and specified. Several hundred detailed engineering drawings had to be produced in order for this device to be manufactured. And I'll point out one clever electronics design feature that was built into this device. If you see the clear view of the device here, this is where the control circuits reside inside this cylindrical piece of the arm. The way we made that work is this circuit board is actually a rigid flex circuit. So it's a three-sided circuit board that's connected with flex circuit material. So it wraps around the battery, which is in the middle this guy, which was a clever solution to make the electronics and the battery fit in this cylindrical format, which is pretty clever. This took about 2 years to go from prototype to design into production. This is another nifty device that is out there. This was interesting because this was not a linear progression, I'll say, of prototype to production, and that's because the market needs were recognized to be changing from when we started. So we probably went through 2 or 3 different iterations of the design of this otoscope. This is a pediatric otoscope. It's designed to have a very small tip, smaller than anything currently out there, that can go into a child's ear canal to image. So we're getting a video image of the ear canal. The purpose here is to reduce unnecessary prescription of antibiotics, because too often mom, dad comes into the ER with a kid that's got an earache. Kid's unhappy. It's not really infected, but antibiotics are prescribed anyway and unnecessarily. So the idea is, hey, if we can actually capture an image of the ear, we can explain to mom and dad why the ear is actually not infected and reduce that overuse of antibiotics. So there's a lot of electronics happening here. There's a very tiny camera. There's fiber optic illumination. You can see, there's a round LCD screen built in. There's a battery. There's an interestingly shaped external plastic enclosure that this is all built around. This was a longer project here for us. Took about 4 years because, as I said, there were some pivots around product requirements. And I'll just give you an example. When we first started, they were convinced that this device needed to have wireless or Bluetooth communication of the image to a smartphone. They thought for sure every customer is going to want that. Well, turns out when we had some prototypes out that they could use to test that feature with prospective customers, they learned that actually no, that wireless connectivity, which added a lot of complexity and cost, actually wasn't really necessary for a minimum viable product. And so we took it out and arrived at this device that you see. And a much more complex device is this one that just recently launched. This is really a fascinating device that does a test for macular degeneration. And there's a lot of optics and electromechanical components here that fit in a custom plastic enclosure. One of the real challenges, there are a lot of challenges in this device, but the diagnostic test has to be done in near total darkness, and you can't quite see in this view of the assembled headset, but there are some silicone rubber, what we call eye cups, that form a light seal around the eyes, so that this test can be done in pretty close to total darkness. A lot went into making that all work. A lot of human factors elements, lots of electronics and mechanical complexity here to make this device work. Briefly, it's like a hearing test. If you've had a hearing test, you hear a tone at ever decreasing volumes. When you hear the tone, you push a button, and what they're looking for is the volume of the tone below which you stop pushing the button, and that is indicative of the health of your hearing. Similar thing happens here, where a flash of light is displayed at a certain intensity. Patient pushes the button when they see the spot, and it gets to a point where the light is too dim and you don't see it anymore. And that the level of light intensity at which your perception does not detect it has been correlated to macular degeneration. So that's what this device actually does. Huge effort around all of this. About 10 man-years of effort over about a year and a half to do all the design for manufacturing work. This one was from a clean sheet of paper, I'll say, but went through a couple of prototype iterations along the way. So there's a couple of quick examples of some of the things that we've worked on in the real world.